This section introduces why a prosthetic hand and a robot hand, though they share one block diagram, are not the same design problem. Both decompose into the same 6 blocks: user input, control, actuator, mechanism, sensor, and power. The whole book turns on why that shared diagram hides a different problem underneath. The difference is whose constraints bind. A robot's arm simply absorbs the penalty of a heavy hand. Only its payload shrinks. An amputee's shoulder and socket cannot absorb that penalty, so mass, kept under 500 grams for an adult and 200 grams for a child, along with an anthropomorphic envelope, become hard limits that dominate every downstream choice. That inversion is the point. The host body, not the task, sets the objective function. It is what everything after this chapter optimizes against. The media's superhand ignores it, which is exactly why physics forbids it. This section explains the single constraint the whole book turns on. A prosthetic hand hangs off a residual limb, so its mass is what a user will accept or refuse, and its strength is beside the point. For an adult, that ceiling is under 500 grams. For a child, it is under 200 grams. Every capability is bought in one currency. A degree of freedom is an actuator, and actuators are over half the total mass. Function and wearability are therefore the same trade-off seen from 2 sides. No grip is added without weight the shoulder must carry. This is budget-dominated design. A single resource caps the system, and its dominant consumer fixes the shape of the trade-off curve. The robotic hand escapes this. A heavier arm merely lifts less. The prosthetic hand lives inside the constraint instead. This section explains what a finger is, structurally, inside a hand you design. A finger is a transmission. Its whole meaning is the map from one motor's torque to fingertip force, and that map is what you design. Chapter 1. Cut the hand into 3 terms: actuator, mechanism, and sensor. This chapter takes the middle term, the mechanism, and shows that its design space collapses to a single lever. Add a linkage, a driven link, a 4-bar, a double 4-bar, and you buy natural curling and a shapeable force profile, at the cost of mass and coordination. Pick a gear ratio, and you trade closing speed against grip force. So the whole design collapses to one nonlinear knob. Geometry is that knob, turned against a single trade-off. The understated surprise is this: force is nonlinear in joint angle, so the link geometry is the force profile. This section explains why a hand is fundamentally a budgeting problem, before it is anything mechanical. A hand's mechanism is an allocation problem. You have a fixed budget of actuators to distribute across the anatomical joints, and each unit is bought at the price of mass and coordination. One actuator opposes the fingers to the thumb, which gives you a pinch. Every actuator you add buys independent motion and richer grip patterns, yet it also adds grams and control burden that the whole device must carry and coordinate. Materials play the same game, one level down, density against tensile strength, where the mass ceiling forces the rejection of candidates that are strong but heavy. That is the chapter's move. Before control, before sensing, the hand is a skeleton-shaped budget, and design is the choice of which degrees of freedom deserve power. This section explains what a sensor is at the most basic level. A sensor is a transduction, some physical variable, a force, a joint angle, a slip, a temperature, is bent into a signal a controller can read. The generative move of the chapter is that the signal side collapses to exactly 3 choices: An electronic circuit stores or dissipates energy in only 3 ways: resistance, capacitance, and inductance. So every sensor is a monotonic function that maps the measured quantity onto one of those 3, R, C, or L. That triple is the whole design space. Pick the property the variable perturbs, engineer the function toward linear, and you are done. The specification is what makes the hand hard, not the physics. Figure 3.1 shows the constraint envelope under 1 gram, under 1 millimeter, under 1 milliwatt. The adversary is that envelope, not the transduction. This section explains why sensing is what turns a robotic hand into a system that knows what it holds. A hand that only actuates is blind. Sensing is what closes its loop. Chapter 3 is where the mechanism earns feedback, becoming a system that knows the object it holds. The compression sits in one line. Every sensor is a physical variable: force, joint angle, slip, temperature, modulating one of exactly 3 passive electrical quantities: resistance, capacitance, or inductance. Those 3 are energy dissipated, energy stored in an electric field, and energy stored in an electric field. The whole catalog: strain gauge, force-sensitive resistor, capacitive, Hall, piezoelectric, is that single map instantiated on different measurements and different physics. The binding constraint is the hand's envelope, under a gram, under a milliwatt, thinner than a millimeter. Predict the next transducer by asking which of the 3 it varies. This section explains how control turns a hand you must think about into a hand that simply obeys. A hand that must be thought about continuously is only actuated. Actuation is not yet control. This chapter's move is to close 2 loops. The first loop is electronic. Negative feedback, shown in figure 4.2, replaces the open loop plant with a servo that corrects its own error. This buys precise finger position despite variable friction and backlash. The second loop is cognitive. It is a hierarchy where automatic lower levels hold grip and watch for slip, so the wearer issues intent. A command like grasp this, rather than micromanaging state. Control is thus the composition that converts a person's command into force, while spending as little of their attention as possible. The same negative feedback primitive recurs at every level. Only the controller's identity changes: silicon below, brain above. This section explains the 4th body, control, the 4th chapter. The chapter begins from a hard fact. Precise motion never comes from knowing the plant exactly. Friction, backlash, and inertia drift. So any open-loop controller built on a perfect model degrades the instant reality diverges from it. The chapter's move is to stop modeling and start measuring. Negative feedback closes the gap between commanded and actual, absorbing whatever parameters you failed to pin down. Then it stacks. A hierarchical controller delegates low-level regulation to automatic loops, so the wearer needn't hold the hand state in mind. They command grip, and the layer beneath watches for slip. The last rung closes the loop back through the human, sensors restimulating skin as haptic feeling. Control is a ladder of error. Correction, each level absorbing the uncertainty. The one above is spared. This section explains how a prosthetic hand gets assessed, and why the assessment measures a person doing a task rather than the device alone. No amount of bench testing, cycling a finger, scoping its currents, tells you whether a hand works. Function is not a property of the device. It is a property of the device plus the person, measured against a task. So the Southampton Hand Assessment Procedure, SHAP, records the only thing that carries meaning: the time a person takes. Here is the move that turns anecdote into measurement. Reduce the infinite manifold of hand postures to 6 prehensile patterns, a basis. Express each as a z-score against a normative population. Then collapse the 6 vector to 1 Euclidean distance. Function becomes a coordinate, the index of functionality, 100 at the norm, decaying as you slow. Given the pattern, you can now generate any grip score yourself. Same Z, same collapse. This section explains how the chapter turns hand function into something you can actually measure. No amount of oscilloscope data tells you whether a hand works. Bench tests measure components, not function. The chapter's move is to make function itself a measured quantity by borrowing metrology's trick. You fix a standard the way the meter was once a platinum iridium bar in France. Here, the standard is the task times of 24 unimpaired people. You collapse the hand's infinite postures onto 6 prehensile patterns. Time a person against each one, express every time as its distance from the normative mean, then take the Euclidean distance across all 6 dimensions. Matching the standard scores. 100. Slower falls towards 0. Function becomes displacement from a preserved human reference, a suitability to task calibrated exactly as length is. This section explains where progress lives once a hand's design is near its physical limit. The closing move relocates where progress lives. Every prior chapter optimized one fixed constraint, a hand's total mass budget, ceilinged by aluminium, 6061 at about 2.7 grams per cubic centimeter. Future directions is that same optimization seen from its dual. Since actuators and structure are near their mass limit, the gain must come from the information layer. Better, since structure are near their mass limit, the gain must come from the inform relocates. Lighter materials, printed metals, and nanofilled polymers by grams. Smarter algorithms spend them better. Vibrotactile feedback closes the sensory loop without invasive cost. The primitive added function is never free. It is always priced in mass, in complexity, and in the wearer's cognitive load. This section explains the constraint that governs Chapter 6, the closing chapter of the book on artificial hands. Every future gain in an artificial hand is bought in the same currency, mass. Chapter 6 closes the book by naming the constraint that silently governed every chapter. More actuators, more sensors, more lifelike motion, an artificial sense of touch. Each buys function by spending against a fixed mass ceiling, that Matspedia Aluminium 606. The density of aluminium, 6061, is the upper bound of what is tolerable. The second ceiling is the wearer's cognitive burden. Control that demands attention makes the hand unworn regardless of capability. So progress is not one breakthrough, but budget recovered, lighter materials, smarter sensing that automates control, and, tellingly, a simple but novel idea may beat any added mechanism. Not a wish list. The frontier